Okay, in the Zoom, can you hear me?
Yes.
What? Okay, good. Right, so let's start today's class. So we will talk about some properties of Wasser's and barycenters, which we started discussion last time. And then for the remaining time, we will start the discussion on the so-called unbalanced optimal transport, which is very cool. Okay, so let's start. So we want to understand some properties of Wasser's and barycenters. So Wasser's and barycenters are defined in this way. We consider the Wasserstein distance, just the optimal transport distance, on the space of priority measures. Okay, and then so now this space is a metric space. Then for any distribution on that metric space, you can consider barycenter, just a metric barycenter. Okay, so Wasserstein barycenter is nothing but Wasserstein barycenter over given distribution, let's say omega, is nothing but the metric barycenter with respect to this Wasserstein metric. And the metric barycenter can be defined in this way. So you just try to find the point in your space. So our space is Px, the space of priority measures. The point is itself a priority measure. So you want to find such a point in that space, minimizing this average distance to those random points in the distribution. Okay, so that is the metric barycenter. And then in some examples, this Wasserstein barycenter has very nice features. Like we consider this example that if you have many images, then you can view these images as a distribution on the space of images. And you can consider Wasserstein barycenter by just considering each image as a priority measure on the space, in the 2D space in this case. Then the Wasserstein barycenter gives this very nice feature, which looks like some kind of geometric average of these shapes. Okay. Okay. Now, so Wasserstein barycenter is like this. Given this data, given omega, the distribution of, let's say, priority distributions, you have this kind of mapping from this omega to this Wasserstein barycenter. Then what kind of property this mapping has? Okay, as a function from omega to this Wasserstein barycenter. Okay, that's what you want to understand. And of course, there are many questions, but probably some of the most important questions are existence and uniqueness. And existence is kind of trivial. I mean, in the sense that minimizer of such problem always exists. For example, if the underlying space X is compact, then the Px, the space of priority measures with respect to this Wasserstein distance, is compact. And then this function, this integral of distance square, is a continuous function on that compact space. So it should have a minimizer. Okay? So existence is, yes.
I did not. My understanding was that, is it true that this probability space over a compact set is compact?
Yes.
Okay.
With respect to weak star topology.
Weak star topology. Okay.
Yeah. Which is the same as this metric topology of this Wasserstein barycenter. Wasserstein distance. Okay. All right. So existence due to compactness of Px when X is compact. Okay. And then the next question is uniqueness. And uniqueness does not hold in general, of course, like it's similar in like an optimal transport case, but if the measures are absolutely continuous, the measures in your distribution. So if these images are absolutely continuous with respect to Rubin measure, then you can prove that the corresponding Wasserstein barycenter is unique. So here this expression means the following. So omega has many random, let's say, probability measures in it, right? Like in here. Then let's say some of them can be very singular, I mean, like Dirac's, but suppose some portion of omega are kind of absolutely continuous with respect to Lubeck. So they have densities. Okay, so that's what this means. So the absolutely continuous measures, the set of absolutely continuous measures with respect to omega has positive measure. That means omega has some non-trivial portion of those element, those random measures nu, which are absolutely continuous. Okay, so under that assumption, you can prove uniqueness. And this assumption is very similar to the assumption, actually it's essentially the same as the assumption in Brennier's theorem, that you need the source measure to be absolutely continuous, then your optimal transport is uniquely determined. So it's kind of, the same principle why we have such an assumption, okay? And then after that, after uniqueness, then you want to understand the features of this Wasserstein barycenter more. And Wasserstein barycenter itself is a probability measure. So then probably one of the first things you want to understand is whether such a measure is absolutely continuous with respect to the underlying reference measure, namely the Lebesgue measure, okay, or not, right? So that absolute continuity is something you can consider. And an example of Wasserstein barycenter is displacement interpolation. You have two measures, mu0 and mu1, and then if you view these two measures as a distribution of measures, right? Like omega is given by just, okay, I should use nu0, nu1. Omega is like the combination of these two measures. Okay, omega is just distribution, okay, of these measures. Okay, then you can consider Wasserstein barycenter of this omega. Then the Wasserstein barycenter is nothing but the point, the measure, let's say nu t in the middle, okay, which is nothing but the displacement interpolation. And then for displacement interpolation, we know that if one of these nu0, one of these measures is absolutely continuous, then something in the middle is also absolutely continuous. So you can actually prove that rather easily. Okay. And here I should be careful here. Or if, of course, if lambda is positive, if lambda is, yeah, we need that. Lambda is, okay, between 0, sorry. If lambda is, in this case, lambda is between 0 and 1. Okay. All right. But of course, Wasserstein barycenters consider more general measures, let's say omega. Okay. Like you can consider many measures in your space of probability measures. Okay, then you can consider the distribution of those measures. That's what this is. What this is. Okay, and then you can consider this on the Euclidean space as the underlying space. Then here you have finitely many measures. Then if one of them is absolutely continuous with respect to Lebesgue, and then the corresponding Wasserstein barycenter is absolutely continuous. And you can generalize this further. You can consider even just any general probability measures. Let's say you can also consider a more general space like Riemannian manifold. But then here is some assumption. So here Now, we just pick some number, and then those measures that are absolutely, hold on a second. Okay, those measures that are absolutely continuous with the Riebeck, but whose density is less than that number L, we consider such as the set of such measures, and then this distribution omega we want to consider a certain barycenter has positive measure over this set. So namely, some non-trivial portion of omega consists of those measures which are absolutely continuous, but whose density is less than some fixed upper bound. Okay, just let me finish my sentence. And then there, in that assumption, you can prove that the corresponding Wasserstein barycenter is absolutely continuous. It has density function. Okay, question.
Is there a line of work that has like K barycenters?
K barycenter means probably somebody. So yeah, let me just translate his question. So K barycenter means you have omega, right? Sorry, you have on the space you have some distribution omega, and then you consider, let's say, not just one the minimizable, just okay, one point which is a barycenter, then minimizing the average distance. But you can consider, let's say, in the same picture, for example, 2 points, then minimize the average distance between the this 2-point distribution and this omega distribution. Then in that case, you have some kind of
Like a weighted.
what is the name of this? Some kind of cells dividing the space, and some portion of omega in that cell correspond to this point, and portion of omega in this cell correspond to this point. So that is, so such a notion is sometimes called K-mean. Okay, and K equals 1 is a barycenter. K equals 2 is higher is called K-mean, and so in general, this K-mean is not necessarily unique, but I'm not sure whether.
What if it was software?
Hold on. I'm not sure whether this Wasserstein barycenter K-mean, Wasserstein K-mean is unique or not under similar assumption. That I don't know, but certainly you can consider such notion of K-mean with respect to Wasserstein distance. Yes.
You divided the space in a sort of in two cells.
Yeah.
But what if they could like be matched softly to the whole space? So it would be matching a simplex to a weighted simplex to the other space through the Wasserstein metric.
Maybe you want to rephrase your comment again. I can understand.
With the K-means, when you divide it up into these two cells.
Okay, right. So
it seemed like
okay, let me draw something. So you have, let's say, px. Okay, so question about K-mean with respect to Wasserstein distance, and then you can kind of divide the space into like some kind of maybe let me draw it. Yeah, so let's say K equals 2. Let's say some new mu1 bar and mu2 bar like this, and then you have this some kind of underlying measure. Okay. Yes.
So what if you didn't divide the space, but you weighted the contribution of nu1 and nu2, or all the way to nu k through the distance in px?
Well, I mean, that's the thing. I mean, maybe I didn't understand that. So whenever you have some weighted whenever you want to find some kind of weighted points, okay, approximating the given omega, you have to you end up dividing the space. That's what k-means do. So maybe I didn't understand your question, but this kind of the partition comes from just nature of k-mean.
Yeah, so my question wasn't about k-means.
Okay.
It was about having instead of one point for the barycenter, having k points, k weighted points.
Yeah, that's exactly what k-mean is. Okay, maybe you can discuss after the class. But certainly it's a good question that one may consider so even further generalization of Wasser's and barycenter. So which is like so k-mean, so not just one single point, but was more just general measures. So that is nothing but this. So here you want to just find a minimizer. I mean, here you have. Okay, let me just comment because it just comes to my mind. Given omega. Okay, so this space has this double Wasserstein distance. Whatever it means the following. So Px has isometric space with respect to Wasserstein distance. So then you can consider the Wasserstein space of the Wasserstein space. Let's call that distance dW. Okay. So you can consider this Px dWW as a metric space. And then there, you want to kind of minimize this distance squares between omega and whatever you measure, or what should be the good notation for that? Let's call it lambda, okay? And then you want to minimize those lambda in some with some constraint. So Wasserstein barycenter is when this guy which is this constraint set, just constrain lambda to be just one single measure, okay, in one single point in Px. So here, so Wasserstein barycenter is C is a set of just the Diracs. Okay, that's Wasserstein barycenter, and K-mean is so Wasserstein K-mean is C is, let's say some lambda j delta j summation j and lambda. These lambdas are okay. Maybe let me move. Oops. These lambdas are relative weights, and then new j's are in Px, and then n is not n, it is k, lambda k. J equals 1 to k. So that k is in the k-mean. Okay. So this is the simplex. I think you were mentioning this kind of nature is a simplex. So you can view Wasserstein barycenter as this just simple minimization problem with this double Wasserstein distance between two measures. Okay, I mean from the given distribution on the space of probability measures over the space of probability measures. Okay, and then you can certainly consider k-mean and other constraint, which generalize the notion of Wasserstein Bari center. But I'm not sure whether there are any papers written for the Wasserstein k-mean. Okay, I'm almost sure, but I didn't see it myself because I didn't search for them. Okay.
Excuse me, Professor. Sorry to
Yes.
ask another question, but
Yep.
it seems like for these first two results by
Mhm.
McCann and Carlier, these are for when omega is basically the support of omega is finite. But then it seems
Yes,
like
that's
this
right.
third, it seems like this third result is just far more general. Like how general are we talking in terms of this omega? Because if previously we've only considered finite supported
Yeah, so
omega.
any probability measure, you can consider a continuous family of measures.
Really?
Yeah.
Okay. Wow.
Okay, other question? But okay, so in fact, okay, you will see that this generalization from finite to continuous family, continuous measures is not that, in some sense, it's not that the big jump, because when you know the law of large numbers, namely any measure, I mean, it's just a meta statement. Any measure can be approximated by finitely supported measures, and you increase the number of these points in the finite support, then ultimately it converts to that given measure. That's the law of large numbers, and because of that, I mean, this jump, in some sense, is not that surprising.
Okay, that actually makes sense. Thank you.
Yeah. Okay. The other question? Yeah, certainly. I mean, asking about this k-mean is a very sensible question. Okay, I like it. Okay. Any other question, comment? No. Okay. Then we can continue. Okay, then let's talk about uniqueness. So for uniqueness, we should consider the functional, which is maybe, okay, let me just consider here. The functional is this. So the functional we want to minimize, okay, so we have this functional to minimize this Wasserstein distance square from, this is good notation for me. Okay, mu. Use mu here. Mu to nu and the omega nu on the space of probability measures. Okay, so we are minimizing this function, right? That is Wasserstein Bari center, and then so uniqueness comes kind of automatically if we knew that this functional is strictly convex. Okay, right? If the function is strictly convex, it looks like this. So you have a unique minimum point. So that is what exactly happens. So if this, okay, first of all, but if this is just integral of these functions. So if this function from mu to this distance, Wasserstein distance square is strictly convex, then this integral, which is sum of these strictly convex functions, can be strictly convex with some condition on omega. Okay, that's what we are going to do. Okay, first, let's check the strictly convexity of this function with fixed nu when nu is absolutely continuous. Okay. So here, in general, this this function, this Wasserstein distance square, is not geodesically convex. Okay, geodesically convex means view this function as a function on this metric space with this metric dw. Then, with respect to dw, this function is not a geodesically convex function. It's not. It may not be convex along geodesics, but here this convexness is just the easier convexity, namely in the linear structure, in the linear sense, meaning, I mean, the like mu t is 1 minus t mu 0 plus t mu 1. So regarding this convex combination in the linear space, okay, we can view just the measures as in this linear space because you can add and multiply these measures, right? With respect to such convex combination, one can prove that this function is strictly convex if nu is absolutely continuous, okay?
What exactly is the convex combination over? We have
Just given two measures, you can just add those measures, right? Multiply, add.
And what's the relation between these two measures, mu
Anything,
0 and 1?
anything, any measures, probability measures, okay? Pick any two probability measures. You can just make this linear combination, right? Okay. Okay, what is convex in the first place? You have some linear convex combination of these two objects, and then what happens to the function? Okay, that's what convexity is, right? So that's what we are doing. So, so basically, I mean, the statement is this. So this is our function, and this is this linear interpolation or linear combination. And then convexity is that this function is, I mean, at this linear combination is less than or equal to this 1 minus t of that function at that one end plus t times of that function at the other end. That's what convexity is, right? So this is a convexity. But here, if nu is absolutely continuous, then you have even strict inequality. That is strict convexity, okay? Of course, this is when these are not equal. Okay, otherwise you have equality, of course. Okay, why do we have such property? First of all, maybe I should ask, why do you have even convexity here in this sense?
Triangle inequality?
No, this is not triangle inequality.
I mean,
It's
doesn't
square.
it stem from the underlying, like if we look at the Benemat-Brenier, the dynamic formulation, then that functional is strictly convex with respect to the velocity of the measure curve?
Yeah, maybe you can consider that, but this should be much more simple than, you don't have to consider Benemat-Brenier here. Okay, the reason is here. So what is W2 in, I'm sorry, the Wasserstein distance square in the first place? Okay, it is, you take the infimum over all transport planes between mu and nu of this, let's say, Cx, okay, so C is just distance square of xy, and here d pi. Okay. Maybe I should be careful here. D pi xy. Okay.
Relate to the linearity and top.
Yeah, so that's what I'm trying to do.
Every visible set in the right hand side, you can combine them to make something in the left hand side, right?
Yeah, so okay, so before I hear you, let me just write this, and then I can come back to you. Okay. Maybe I should. Okay, let me erase this. And oops. Okay, I can hear you now.
Any transfer plane from mu0 to mu and mu1 to mu. Using the 1 minus t and t, you can construct a transfer plane from 1 minus t mu0 plus t mu1 to mu. So the right hand side will always be an upper bound for the left hand side, even the way to be even more the right, because the transfer plane in the right hand side can be combined to make the transfer plane with the left hand side. So it's fine. Go on.
Yeah, so okay, I think I mean, better strategy for answering this question and taking your comment is to give it as your exercise, okay? Because I don't want to just confuse you further here. So to show that mu is convex, okay? Okay, what about this? Okay. So it's your exercise, okay? Maybe James mentions basically the idea, but I want you to do this yourself, okay? Okay, then why do you have strict inequality here? Okay, let's focus on the strictness, okay? But okay, so just back to my comment over other suggestion is that this exercise, for this exercise, you don't need Benham linear at all. It's just a simple analysis, okay, simple manipulation. Okay, why do we have then strictness? It's like this. So consider these two mu0 and mu1 given as two Diracs. So mu0 is a Dirac, mu1 is a Dirac, and nu is this absolutely continuous measure. Okay, then optimal transfer plane between nu to this is just this matching. So everything goes there. And optimal transfer from nu to that, it's just this matching, everything goes there. And then if you do, actually this kind of answer is partly the answer to exercise. Then if you consider the transfer plane, just taking the linear combination, like 1 minus t pi 1 plus pi 0 plus t pi 1 here, pi 0 transport mu 0 to nu, sorry, the other way around. It couples mu 0 and nu, and pi 1 couples mu1 to nu, okay? So then there, if you take this linear combination, then obviously such cost, if you take the cost, this is again a transfer plane between this and, okay, now I should say, and this is a transport plane corresponding to 1 minus t mu 0 plus t nu mu1 and nu. Okay, so this is transport plane between these two. And then the cost of this, let's say cost, I mean integration of this measure with for this cost function can be, is a linear structure, right? So you have the sum of these two costs. Okay, but this cost is bigger than or equal to the transport cost between this and that. Making sense? Anyways, that's the reason. So the cost of this is bigger than or equal to the optimal transport cost between this and that. But actually, the optimal transport is like this. If you do optimal transport, then with this measure to this, then it's kind of similar to my comment on this k-mean, that you divide this region into two, and this half goes to there, and this half goes to there. Let's say if t is half, okay? And then if you consider on this, then let's say points here, which previously goes there, but now it goes here. And as you see in this like a picture, which is rather precise, this distance is much small, and not much, small, strictly smaller than this distance. Okay? Making sense? So that's why, I mean, you have, by matching this to there instead of going there, and these points going there, you have, so you have all these kind of matchings, which are now these matchings, and then these lines, segments have smaller lengths than this. That's why this one has strictly smaller transportation cost of the distance squared. Okay? Yes.
What happens when nu is a Dirac right in between them?
Right. So that's a good point. So here,
And in general, like
the thing is that this happens because nu is spread out. So nu is absolute continuous, so it has like a spread out. So that's why you can just kind of divide this region into the two, and then this kind of strictly small distances appear. But if nu is just let's say if nu, okay, so if nu is just, if this was nu, then it's the same, right? So here, this one matches to there, this one matches there. And optimal transport is just this one goes there, this one goes there, and half weight. Okay? So same. Okay? Is strictly better than A. Okay? So that's why the singularity of measure may not have such strictness, but it still has the convexity. Right? So we have strict convexity of such function distance square or certain distance square when whenever this measure nu is absolutely continuous. Okay, and now our functional to minimize is just an integral of that with respect to omega. And so, okay, if this nu, let's say if every nu in this distribution of omega is absolutely continuous, then this function is strictly convex. So you choose integrate strictly convex function, you have strictly convex function. That's why you have strict convexity. As long as you have, let's say, non-trivial portion of this omega being absolutely continuous. Okay. Question? Okay, so actually, I mean, this is the same reason why in the Brownian theorem, when we have absolutely continuous source measure, then the corresponding optimal transport is unique. Same reason. Okay. Okay, so let's move on. Then an absolute continuity. So here is an example. So Mekan's interpolation, given two measures, you can consider the transport between them, and then you just look at those, what happens in the middle. That's Mekan's interpolation. And if one is like this absolute continuous measure, like this ball, and the other is like kind of very singular measure, like this Dirac, even though this measure is very singular, if the other end is absolutely continuous, then as you see in this picture, the something in the middle is still absolutely continuous. Okay, that's what happens. Okay, just simply because even if this is very singular, I mean the mass is very concentrated in a very small region, but if the other one is spread out, then when you do the interpolation, you have to spread out this mass at least a bit. That's why you get absolute continuity. Okay, that's the reason. But of course, you can apply this. Actually, we actually treated this when we consider absolute continuity of Mekan's interpolation. We already did. Just using that, the mapping, let's say, from here to, from the interpolate measure to the other one is to the other one is Lipschitz mapping with a bounded Lipschitz constant. And so, for example, if this was in the when just in the middle, then Lipschitz function has Lipschitz constant 2, and then you get this density upper bound given by 2 to the n of the density of this the other end. Okay, anyways, so we did this, and essentially this is what captures the nature of such absolute continuity when we have two measures. Okay. And when you have not just two, many measures, okay, in the space of plurality measures, and one of them is absolutely continuous, and the other one, let's say, are all singular, then what happens? Okay. Okay. So in Rn, you can do this rather nice analysis that you can consider this kind of barycenter mapping. Given the set of points with this weight lambda I, okay, this xi's as points, and then we have lambda i's, then you can consider the barycenter of such distribution on your underlying space X. So that is what the C lambda is. But such barycenter in this case, because in the Euclidean case, is rather simple. You just take this sum of these, weight this sum of these points. That is what barycenter is in the Euclidean case. Okay. But then you can consider from the Wasserstein barycenter to, so I have to, so here is like this. You have, so it's just in 2D case, let me just draw the 2D case. You have this pi star, which is like an optimal transport plan between two measures, mu1, mu2. And then what this mapping does is just given x, so it's just when n equals 2, given this x1, x2, okay, and then let's say lambda 1, lambda 2 is just half. Okay, it sends this point to this diagonal. So it's x equal y, like this. So it's just x1 plus, okay, x. So let me draw it again. So you have this diagonal set, which is x1 is equal to x2, and then you just send your transfer plane between these measures, which is given on that product, which is given as the probability measure on the product space. Then you just project it to this diagonal by sending to this the body center points of this combination. Okay, so then if you further project it down to underlying space, after this you just take this part, then that is what Wasserstein body center is. Okay. Note pi star C lambda. The push forward is the Wasserstein body center. Or omega, which is a summation of this Diracs. Okay, so okay, these are U1. Okay. Maybe I don't want to confuse. So just ask me any question up to here. Okay. So let me try to rephrase it. So last time we briefly saw the connection between the Wasserstein body center and the multi-marginal problem, multi-marginal optimal transport problem, right? So let's say this pi star is a solution to this multi-marginal optimal transport problem, which gives some kind of transport plan, a probability measure on the product space, having coupling those different marginals, okay, nu1, nu2, and so on, nu n, right? And then what Wasserstein body center is, after solving that multi-marginal optimal transport problem, you just project that by this body center map. Then you get the Wasserstein body center, okay? Okay, fine. So that's what you have. But then this one, this mapping actually has an inverse. So you can take the inverse of this mapping going to the support of this thingy, the pi star, which is a solution to optimal multi-marginal optimal transport. But that inverse map has this ellipsis bound. Okay, and then which is something you can prove, and that ellipsis bound is actually the same as this two marginal case. Okay, in the two marginal case, the map from the Wasserstein body center to the mapping, which is basically the mapping from this diagonal to these points on the support of the optimal pi star, has this ellipsis bound. Okay, and then because of that ellipsis bound, by the same principle regarding how the ellipsis map change the density of the measure, you can get the density of Wasserstein body center is bounded by density of, for example, one of these marginals, in particular nu1. So if nu1 is absolutely continuous, then this one is, I mean, that means this is, if this is finite, then of course this one is finite. So that's why how you can rather easily find this absolute continuity property. Okay, and this estimate is exactly a simple generalization of what is seen here. So here you just consider the mapping from here to there, and that mapping is basically that mapping is basically C lambda inverse, okay, where lambda is just a whatever the proportion is, in this case, lambda equals 2, sorry, C half or inverse, that's what this is. And then this mapping is ellipsis. In this case, the ellipsis constant is, I think, 1/2. Sorry, ellipsis constant is 2. So that's why you get that. So then you have the same thing here. Okay.
Excuse me, I have a
Alright.
question about this.
Yes, yeah, thank you. Yeah.
So when we define the inverse, right? Because it seems like this inverse would not be a function in general, but we're restricting the codomain to the support of pi star. And then we can ensure because it's
I mean, it's a function. I mean, it's just you don't have to consider this. It's just a mapping from there to that whole space. But the point is that the image from this is exactly this.
right. I guess like just in the case of Rn, right? Like if we look at the C lambda which is provided, like this is definitely not like a bijection from Rn to R. So I guess to
Yeah,
define
there's
the
no
inverse,
bijection from Rn to R, right?
yeah. So, but I guess we're defining the inverse because there is a unique point on the support where we can, I guess, yeah, when we restrict to the support of pi, then this C lambda is injective from support of pi to
Okay. So you got confused because of this notation, right? So just yeah, okay, I see what you mean. Yeah, you are right. Okay, sorry, I take back. Yeah, right. So you just consider this inverse makes sense only considering this. Yeah, sorry about that. Yeah, you're right.
Okay.
So in other words, okay, so just to rephrase myself, in other words, this projection, okay, so you have this projection from, let's say, R2 to R. Of course, that is not injective by itself, right? Because it's just projection. But if you restrict that projection on the support of this pi star multi-marginal optimal transfer plane, then that projection is 1-to-1. Make sense? So in other words, okay, note C lambda restricted on the support of pi star is 1-to-1 almost everywhere. Pi star almost everywhere. Okay, so almost every pi star points here, their projection is 1-to-1. So then you can consider the inverse. Yeah, thank you. Is this more clear now?
Yes.
Yeah, okay, thank you.
So this would use some regularity theory from multi-marginal optimal
It
transport
does not
to
use regularity theory, but it used this is the property of optimality of this pi star. So
Okay.
which is in let's say in two vanilla case, which is the same as cyclical monotonicity or pi star. Okay. Other questions? Okay, now, then in general, we do not have such a linear kind of structure for more general, let's say, metric spaces like Riemannian spaces. We cannot just add points in the Riemannian space. So we do not have this kind of thingy, but you can still consider something similar, okay? But here, one way to consider it is this. In general case, this picture still holds. You have one Dirac and some absolute continuous one, then the barycenter, Wasserstein barycenter should be absolutely continuous. But then here, not only that, you can actually estimate the density, the density of this middle one, okay, by some constant, up to some constant C by the density of the other one. So this C depends on, okay, I already wrote here. The C depends on the property of the underlying domain, like a Ricci curvature, diameter, dimension, whatever. Okay. So then you have this estimate for whenever this the other end of the interpolation is just a single Dirac. Okay. So you have that. See you. And then the idea is when you have, let's say, okay, let me just copy. When you have, let's say, more general measure here as your mu, okay, mu 2, and this is mu 1, okay? Then you have, I mean, okay, this is general measure, but you can approximate this measure by sum of Diracs, okay? Like here, okay? Okay, then what happens is, for the sum of Diracs, you have okay, maybe I should you have the following feature, namely, let me draw it again. For this, you can actually, okay, let me just copy this. Oops, okay, never mind. Okay, you have these points here, and these points match with some part of, okay, let me draw it again, sorry. What? So here, let's say new one is like this, then it's like the similar to this K-mean case. So each of these points can correspond to some part of this this measure. So this one corresponds this, and this one corresponds to the other, and this one corresponds that, and this one corresponds with it. So you kind of divide the measure into this kind of partition, and each part, let's say this one, and this one corresponds to this part, and so on. Okay, and then for each such correspondence between these partitions, if you consider Wasserstein barycenter, you have something in the middle which are absolutely continuous. Just the same feature as before. So this you have this picture for each of these partitions. So then the resulting one is absolutely continuous, and you can actually have the same estimate as before. Okay, then you take the limit. Then you can just consider that in this two marginal case, the Wasserstein barycenter, which is nothing but Mechanis interpolation, is absolutely continuous. Okay. Now, what if we have more than two marginals? It's like What if we have more than two marginals? So you have, let's say, new one, new two, new three. Okay, let's consider three case. Okay, then the same here, you approximate each of these measures by Dirac, while you can keep, let's say, one of them the same as before, okay? And then what happens is, when you do this Wasserstein barycenter between these, then what you get is this, between these point clouds, okay, what you get is you have some kind of, still, you can combine this one and this one corresponding to some portion here, and let's say this one and this one corresponding to some part here. So you still have, it's kind of similar. You still have similar partition structure as before. This one and this one corresponding to, let's say, this partition here, and so on. Because you have more marginalized, the number of partitions here will be more bigger. I mean, this partition will be more complicated because you have different combinations to match with these points. Okay. So, but the thing is, still, you have some kind of correspondence between this and this and this. Okay. But then what you have is some kind of when you do the Wasserstein barycenter, what happens is that you have, okay, so I have to be careful with this drawing. You have some kind of portion coming from this and this, and another one. Okay, sorry, let me use a different color. Okay, the same color as this. So this one are kind of matched in the middle in this way. This one goes there, and this one goes something. And then, for example, this one, it goes, they are matched in this way. So also this one. Okay. Do you get some idea? So my point is that if you do this, you will have in the middle for the Wasserstein barycenter something absolutely continuous. Of course, I just drew the picture, I mean, in such a way, but you can actually prove it. But this step is not so trivial. Then this Wasserstein barycenter with this, let's say, this discrete mass for the other marginals, we still have this density upper bound by this absolutely continuous measure, new one. Okay, and after that, because this C is independent of the number of points here, number of points here, you can just take the limit. Then everything, this one will converge to the Wasserstein barycenter with this density still less than the same thing. Okay. Yes.
The final result has mu1, but it seems like it should be symmetric. Although the proof treats mu2
you mean this one?
and mu2 to nu n, yeah.
Yeah.
As having these like finite
Yeah.
directions.
Yeah.
But it seems like in the end we have this asymmetric result because it should be any mu I.
Yeah, that's a very good point. Yeah, so here, what is special about new one? You can choose any absolute continuous marginal. Okay, I just choose this absolute continuous marginal having this density upper bound. So when you have it, then you can just do this.
Does the curvature only relate to that?
The curvature is only for the underlying space. We have the same underlying space for all these other marginals. Okay, so X is just given.
So this holds for any a density that's absolutely
Yeah,
continuous.
so you can just pick your new one as the one. You can just pick any absolute continuous marginal as your new one. Then you can do this. But of course, this analysis assumes that this one is kind of bounded, right?
Yeah.
So that's why we, at least in our paper, we need that condition that this, this L, this density is bounded. This condition actually came from that analysis because we kind of needed this upper bound. Okay. All right, then you can generalize this to more general measures. Okay. Any question? James, any question? No?
So when you draw this figure here,
Yeah,
you're thinking of this multi-marginal, so you're thinking about this Berry center.
right.
You kind of have some intuition about a dynamic form of the multi-marginal optimal transport, almost like, because I guess when I visualize the
Yeah,
the two marginal case,
yeah.
right, there's this dynamic intuition where we move from one, we
Yeah,
follow
yeah,
the displacement interpolation.
yeah.
Does that intuition still hold in this multi-marginal setting?
So here this dynamic thingy is like it's like something like you have a time, right? So time 0 you have somewhere, and time 1 you have somewhere. That's what happens here. Time 0 and time 1, right? Here, let's say if it's time 0 is like this, then of course, then this portion corresponds to these 2 points. Okay, it's not like you are splitting the mass to the 2 points. It's just every point here is matched to this point. So you have this, let's say, x1, x2, x3, which are matched together. Okay. So then this dynamics is like you have triangle. You have x1, x2, and x3 matched together. You have kind of triangle. Then you pick something in the middle. Okay, and that is what this that gives you this kind of points here. Am I making sense? Okay, maybe okay. It's a very good question what you asked. Do I have any space? Okay, it's kind of okay. It's not exactly the same as what I drew there, but it's like this. You have x1, x2, and x3 that are matched. Okay, so here this partition set means these points are matched with this particular x2 and this particular x3, like here. Okay. Okay. Then depending on your lambda, you have this kind of simplex between x1, x2, x3, and then the barycenter map gives you that is this point C lambda x1, x2, x3. Okay? Right? So of course, if you change lambda, you can pick this point or that point others, right? But the point is that if you fix lambda here, then this combination gives you this point. But you have these other points in the cell. So different points will make different simplex, and their corresponding center are different, right? So if you have this family of these points here, then you have corresponding family of these triangles and the corresponding family of this center of the triangle. Then that's why you get this kind of shape. Okay. Am I making sense here?
Right. So the intuition is like we can try to visualize this. We can try
Yeah,
to
moving
visualize.
one of the arms of the triangle, then how the center moves. The center of the triangle moves as you move one of the arms of the triangle. Okay?
Okay, yeah, that's helpful. Thank you.
Yeah. I think it's a very good question. So otherwise, I wouldn't explain this. Okay. Yes.
How should I think of the infinity norm? Is it different when it's over a density?
Infinity norm is just the density. It's just the density. Yeah.
It's just the max?
Yeah, maximum of the density. Yeah. Okay. So I don't think I have time to cover unbalanced optimal transport today. It's a pity that I spent a lot of time yesterday to prepare the lecture for unbalanced OT. But anyways, let's just keep doing it. Okay, then, so now we know the absolute continuity of Wasserstein body center, maybe under some condition, but very general conditions. Okay, and then the next question could be then any further property. So remember, we view this Wasserstein body center as a function from omega to the corresponding Wasserstein body center. Okay, so suppose your omega has some nice property. Then omega consists of very nice measures, like very smooth and very nice shapes. Then what kind of nice properties this Wasserstein body center can inherit? Okay, so that is kind of the regularity question. So if your marginals are very nice, then would the Wasserstein body center also be nice? And nice in the sense, for example, like smooth. If these are smooth distributions, would that body center will be smooth as well? Okay, so the regularity question is something you may want to ask often. Okay, let's consider that. And let's start with the two marginal case. So if you have two marginals, nu0 and nu1, then of course, Wasserstein body center is nothing but Meccans interpolation. Okay. Okay, then what happens is this: you have nu0 and you have nu1, and then you have in the middle, you have let's say nu bar, which is the Wasserstein body center of this omega. Okay. Then how can you understand regularity of this thingy? And the idea is to consider Monge amplification. Okay, given these two distributions, we have the corresponding Monge amplification, and optimal transport is nothing but the solution of this Monge amplification, and right, you can just take the gradient of the solution to this Monge amplification. Okay, and then whatever nice properties of this optimal transport will be related to, this solution to this Monge amplification will be related to the properties of this data, rho 0 and rho 1. Okay, fine. Okay, now this nu bar, this Meccans interpolation, let's say if its density is rho bar, has this property, namely, you can view this measure as your target measure from nu0 to that measure. Okay, then you can consider the optimal transport between them. But that optimal transport between these two is nothing but a proportional version of the optimal transport between nu0 and nu1. Okay, so the corresponding Monge amplification can be written in this way. So this u is the same as this u, but then between these two measures, the original nu zero and this Metcalfe interpolation, the corresponding optimal mapping is nothing but this one. Okay. And then you have this equation. Okay, that is what we have. Okay, that is what we have. And then what we know is that if rho 0 and rho 1 are very nice and good, then this U is very nice and good. I mean, very good. I mean, it's smooth and regular, whatever, right? So that is like regularity theory of Monge application. If the data is very nice, then the corresponding solution, in this case U, is very nice, like smooth. Okay. Then you can use that information here to consider this, to derive information of this rho bar, right? Fine. For example, if U is like smooth, then Hessian is smooth, so the determinant is smooth. Okay. So then this is smooth. So this is smooth. And if rho 0 is smooth, this is smooth, this is smooth. Then rho bar, which is given by this equation, if this is smooth and this is smooth, then this one has to be smooth. So you can apply this Monge application to derive smoothness of rho bar when you know smoothness of U and rho 0. Okay? So two marginal case, it just boils down to regularity theory of Monge application, and which has a very long history. I mean, yeah, in particular, Kapala's work is very famous, and then for more, so these are for CXY, just Euclidean case, okay, and for more general case like Riemannian manifold case, we do not have such regularity theory in general, but we have it in a restricted manner. Namely, you have some conditions on the Riemannian manifold or your cost. Then under some conditions, which we call now Schrödinger 1 MTW condition, whatever it is some condition on the cost function to get regularity theory of the optimal transport mappings. Under such condition, we have some theory. So we have regularity of OT mappings. If you are interested in this direction, then there are several survey papers. I wrote one, but also Figari wrote one, and so on, and Meccanos wrote one. Okay. Also, they consider this so-called partial regularity. Then, if your data rho 0 and rho 1 are not very nice to have regularity, but some kind of defect, some conditions are not satisfied, then what happens to the corresponding solution? Or can he identify the nature of the sets where the solution is not smooth? That is called partial regularity theory. Understand the nature of singular set where the solution is not nice. Okay? And this partial regularity theory is also considered by Figari and myself, also Di Filippis and Figari, and also many others. But this is rather, I would say, still underdeveloped direction. But this research direction seems to be very difficult to make any progress. Okay. Okay, so that's two measure case. Then if you have more than two measures, let's say you have three very nice measures, then what happens to the Wasserstein barycenter? Okay. What is your guess? Let's say you have smooth measures, smooth and nice.
It's
Everything is
smooth.
just
Yeah, it's smooth.
how do you know that?
That's my guess.
Yeah, right. So it's intuition. Yeah, it's somehow. I mean, I agree with you. I would bet on smoothness. Okay, but the thing is, this is unknown. This is an open problem. So if you can handle this problem, please let me know. Okay. There's one approach you may possibly apply to this problem. You can still try to use Monge application between for the optimal transfer between this barycenter measure to the other measures. Okay, you have let's say some optimal map like greater than phi to optimal map greater than phi 1, optimal greater than phi 3, and these optimal maps have Monge application. Okay, given in this way. These are rho i's are the marginal densities, and rho bar is the density of the Wasserstein barycenter. I suppose your marginal densities are smooth, and if we knew that ui's are smooth, the solutions are smooth, then this is smooth, so rho bar should be smooth. Okay, but the thing is, we do not know smoothness of ui. You cannot apply the usual regularity theory of Monge application because we do not know about this rho bar, right? Okay. So you can apply the regularity theory of Monge pair. But one possible thing you may use is the thing. So when you have, let's say, this this new 1, new 2, and new 3, and you have, let's say, this Wasserstein barycenter, let's call mu bar. Then one thing is that almost every x bar here the optimal transform map from mu bar to nu 1 and mu bar to nu 2 and mu bar to nu 3, they have very nice relation. Namely, it's very nice relation, very natural relation. Namely, okay, I should use, sorry, this u. At each point, these vectors corresponding to this displacement, okay, is balanced. Namely, this vector sum is 0. Okay, so I have to be careful. So here, so this vector sum, this point, if you take average of this, then you get just x bar. That's it. So I should. Okay, I should say this. Okay. So that is the condition we have. So then we now have a system of equations. System of Monge application with these different marginals and with this condition. So this is a system. And then if you can handle this system, you can answer the previous question about the smoothness of Wasserstein barycenter. Okay. And okay, anyways, I'm over time, so let me just take 3 more minutes. Okay, then before closing the lecture, I'd like to mention that this Wasserstein barycenter business also has this regularization aspect. You can consider this entropy regularized Wasserstein barycenter. Okay. Then, namely, for your barycenter measure, you just put this like a penalty function so that the barycenter measure has to be absolutely continuous. So then if you solve this, of course, your barycenter measure is absolutely continuous and you have very nice regularity theory here. Okay. So you can have this regularity or nice properties of this Wasserstein barycenter if you regularize the problem in this way. Okay. And also Caesar in 23 considered even the regularizing this part with the entropy regularized optimal transport cost, right? So this is just the entropy regularized optimal transport cost. Then here, of course, you can have even better property. And here, the better, probably one of the most important benefit of considering this is the computational effectiveness. So in this case, you can compute this in a more effective way, but also you do have more additional features. So if you are interested in, then you can check this paper and also this paper for this aspect of regularized Wasserstein barycenters. Okay. So I think I have to stop. Thank you.
Thank you.
Thank you.